Hello and welcome everyone to a course I'm calling second course in calculus, dynamics in disguise. We'll see that dynamics show up eventually. Really, you should think about this as a calculus 2 course. So we're assuming you have knowledge of integrals and derivatives, algebra, trigonometry, etc. But actually, as you'll see, we will cover a lot of those topics in the beginning chapter as well. So I have this nice little quote right away. It says, "Mathematics is a game. You win by making the craziest statement possible. There's only one rule. You cannot lie." And this is really the approach we're going to take to motivate a lot of what we'll be doing throughout this series. I've written a foreword here where I just kind of describe what to expect from the text, from kind of the entire course, and as well as the rest of the book. So we should think about this as a sequel to a first semester calculus course. And we use this subtitle, Dynamics in Disguise, because the mathematical field of dynamics can really serve as a MacGuffin. A MacGuffin is film and media studies term, which refers to a device which kind of propels the story forward or the plot forward. It's something that the characters pretend like they need to achieve, but in reality the actual meaning, moral, and plot of the story is different from the MacGuffin. But we're kind of thinking about dynamics in this course as our MacGuffin, some way to help us motivate what we're learning. Now, what do I mean by dynamics? Dynamics is really the way that we predict the future in mathematics. So that's where we use mathematics to predict the future. And we're going to get there eventually, and then we're going to finish out. It's going to give us an excuse to study some two-dimensional problems, and then we will actually finish out with techniques of integration and the Taylor series, which are very common topics included in a second semester calculus course. And then at the very end, we'll kind of talk about arc length, general areas, and general volumes. Those three terms don't really work with dynamics as well, so we've saved them to the end, and they'll eventually show up. But they don't work with our MacGuffin, so great. So it's kind of like we're going to MacGuffin our way through dynamics until the very last chapter, and then we'll cover some other topics that are kind of expected out of a calculus 2 course. So at the end of each chapter, if you have access to the text, you'll see this at the end of each chapter. We've got our exercises, and I've split these into 3 subsections, which I'm calling apprentice, journeyman, and master. In fact, I do have the 4th subsection, genius, but let's not consider those for now. So apprentice, journeyman, and master, those are kind of the ranks you can achieve in the trades. Apprentice is when you're overseen and you're asked to perform somewhat minor tasks to make sure that you're training well to actually have the ability to perform some maybe more complex tasks on your own. And that's where the journeyman comes through. So a journeyman is kind of the classic trade rank where you are perfectly allowed to perform the trade yourself. You don't need anybody looking over your shoulder. And this is where, within the book, if you get to these journeyman exercises, you should think about the journeyman exercises being the ones that are going to be expected of you if you leave the course and pass the course. You're in some future course or your career, and somebody notices on your transcript you've passed a calculus 2 course. These journeyman exercises are really what they're going to be expecting out of you to be able to complete. The master exercises, which follow that, really should just be thought of as nice fun exercises for readers maybe who are thinking that the earlier exercises, apprentice and journeyman, are mundane. So they're a little bit more exciting, but also quite tricky. You have to really delve deep into the mathematics, and particularly if you think maybe mathematics would be a good career choice for you, I would go ahead and look at those master exercises. And then finally, the genius. There's going to be exactly one genius exercise per chapter, and that's almost always going to be unsolved problems that I couldn't solve myself, problems that probably 99.999% of the math PhDs in the world cannot solve, because nobody has solved them yet, except for, I guess, there's one situation where they have been solved. That's this one at the end of the first chapter, which is from O's last theorem. So that one was solved in the 90s, but I put a little caveat on the exercise that says you can't use any math that's been developed after 1990 to answer the question. So they all should be interpretable once we finish the chapter, all these genius exercises, but it's really just something to look at so you have an idea of really where the current cutting edge of mathematics stands. So with that, let's move on to the first section of the book, really the first chapter, which I'm calling mathematical literacy. And the first section being the language of mathematics. So please allow me to wax poetic, maybe wax philosophic for this section, because I think it kind of founds all of mathematics from my particular perspective. Maybe not that many other mathematicians' perspective, but mine, and hopefully it helps motivate you as we complete this course. So what do I mean when I title my chapter mathematical literacy? Well, literacy is defined as the ability to read, write, speak, and listen in a way which lets us communicate effectively and make sense of the world. And so what I mean by mathematical literacy is to do all these things mathematically. We want to mathematically read, we want to mathematically write, mathematically speak, and mathematically listen in a way that helps us communicate effectively and make sense of the world. This is not an easy task because, gaining English literacy, or whatever your native language may be, is already a difficult thing to obtain. I mean, we spend many years of our schooling learning English literacy, learning to read, learning the alphabet. But on top of that, we're inundated on a daily basis with this language, with English. All of our media is, and I'm going to assume that the listener has English as a first language, but whatever your first language is, we have all of our media, all of our communication with each other. You open up your phone and you're reading articles, and that's all in English. You're watching TV, that's all in English. You're speaking with each other in English. And even so, literacy is hard to obtain. Can you even imagine with mathematical literacy how hard it is to obtain? So I kind of do have that luxury as a PhD to be inundated in mathematics, and so I personally gained this literacy that I know is difficult for others to obtain. But we're going to try to build it, right? I think this is the perspective we should have, is we should try to build this mathematical literacy, even if we're not going to be perfect at it. Same way that there's a lot of vocabulary in English I still don't know to this day. But we can get better. We can always get better at kind of understanding things a little bit more than we did yesterday. And to that end, let's reapproach this quote that mathematics is a game. You win by making the craziest statement possible. There's only one rule: you cannot lie. Let's think about how powerful this game may be if we cannot lie. It means that no matter what statement we make playing the game is a fundamental truth. It might be crazy, right? Kind of the whole point of the game is to make this crazy statement. But whatever statement we make, if we're making it within the game itself, is a fundamental truth of the universe. And so 1 + 1 = 2, very natural, everybody's favorite mathematical statement, falls within the game. Maybe not the craziest statement possible. You're not going to win the game with that statement. But you just learned something that is fundamentally true. It can't really be falsified. And what's important about this is the moment we find a crazy statement, even if it feels particularly odd, if we make a crazy statement that is actually relevant to the real world, maybe by accident, but maybe on purpose, such as this one here, once we make a crazy statement that's actually relevant to the real world, we've gained knowledge and power. This is the Lagrangian for the standard model of particle physics. And, physicists spent a lot of time studying math so that they could come up with this Lagrangian. And once they did, the amount of truth we learn is just astronomical. It's out of this world. Because there are statements that this makes that just can't be false. In the moment it can't be false, we have immense power over predicting the future. And so in some ways, this Lagrangian of the standard model is what allows us to construct transistors, which operate our phones, the solar and nuclear energy, which powers it, the radio wave transmissions, which communicate with it, and even the LEDs on which it communicates with us. All out of some mathematical statement that maybe felt like it got pulled out of thin air, but because it was the truth, we knew it had to tell us something that could never be false. Let's move on to this next subsection, which I call mathematical lexicon, grammar, and semantics. You may have heard those three words used before, maybe not. But they have a meaning as a subset of all languages, including, in my perspective, the mathematical language. So a lexicon, also known as vocabulary, I just think the word lexicon sounds cooler. That's why I'm using it. A lexicon is the total collection of words that we're allowed to use in a language. The grammar is the collection of rules which the words have to follow within the language. And then the semantics is kind of the fun part, which is where you get to interpret the actual statements inside of the language. And we really can think about this mathematically as well, but let's just take a quick aside and understand what it means within the English language. I've got this example here, I, my dog, which is an invalid English statement, even though it uses perfect English vocabulary. It just doesn't follow the grammar of English to be a meaningful statement, as compared to I walked my dog today, which does follow all of the rules of English grammar. So we've got these 3 words in English, which are all part of the lexicon, or in my second case, 5 words in English, all part of the lexicon, which all, mean something, but when you put them together according to the grammar, they actually have a broader meaning, which we can interpret semantically. That's the point of the semantics, is to actually gain an interpretation of I walked my dog today. That means something about the physical world or our experience, as opposed to I, my dog, which doesn't quite mean anything. And partly that is the kind of the interaction of grammar with semantics, is that you have to be grammatically correct to be semantically interpretable. I mean, there's some subtleties there where you can get away with some things, but nothing perfect. And I do have some examples within my prose of the mathematics operating under these similar sets of lexicons, grammar, and semantics in math, because we have something like 1 + 1 = 2. That's a collection of 5, if you interpret it correctly, 5 symbols, which we're going to think about as words in mathematics. And it's a perfectly valid collection of these mathematical words. So it follows the grammar, because 1 + 1 truly does equal 2, and we're allowed to associate a semantics to it, which in some sense we like to interpret as 2 individual objects, merging them together into a larger singular object which contains both of the originals. So there's some notion of combination when we're talking about addition, and what does 1 and 1 mean? Well, it's a combination of singles into kind of a double, whatever that idea of the double is. And so, mathematical literacy is kind of gaining this understanding of mathematics as a language, where each symbol represents something, and then a correct collection of symbols which follows the grammar has some sort of interpretation outside of that. Now, sometimes I do say that mathematics has the ability to remain purely lexicogrammatical. I made that word up. I don't know if it's actually a real word, but what I'm saying is that sometimes we don't really have a semantics to associate to mathematics. A good example here, a monad is a monoid in the category of endofunctors. We can't really understand that in any sort of physical reality, but mathematics still allows these statements to be included within it. So we're not going to worry about statements like that. I mean, that's something for PhDs to worry about, and even I don't worry about monads being monoids in the category of endofunctors, but about 5% of PhDs probably would. But they don't have like a real world semantics that they associate to that. They kind of are interested in it for its own sake. The same way you would be interested maybe in fiction in the English language, because there are good lessons to learn from studying things which can't actually be real in the real world, right? We can still learn lessons by studying these very abstract objects, even if they don't have some sort of instantiation in the real world. Well, anyway, I have provided an example of a valid grammar in mathematics and an invalid grammar in mathematics, because at least according to my definition, the valid grammar means that the mathematical statement is true. So here we've got a mathematical statement, a plus b quantity squared equals a squared plus b squared. This is just not a true mathematical statement, so I'm going to say it's an invalid grammatical statement as well. And why doesn't it equal a squared plus b squared? Why can't we distribute this 2 to both terms? That's called the freshman's dream, by the way, even though it's not true. Well, if we go ahead and FOIL it out, right, a plus b times a plus b, that's the definition of a plus b squared. Well, you just go with the first multiplication of the first terms, a and a squared, multiplication of the outer, a and b, multiplication of the inner, b and a, and multiplication of the last, which is b and b, we end up with a squared plus 2ab plus b squared. So from my perspective, mathematical grammar requires that mathematical statements be true for us to actually make them. And I think that's quite useful, because it makes us think that it's no longer the case that we screwed up mathematically when we write something down false. It's just that we didn't follow a grammar, right? We're grammatically incorrect, and so we just need to update our grammar until it's correct. That's kind of a nice interpretation to take of these mathematical statements. So moving on, I want to talk about these equal signs that have been included in our mathematical statements. And actually, if I move back up to the first time I talked about mathematical statements, 1 plus 1 equals 2, or a monad is a monoid in the category of endofunctors. If I just look at these specific symbols of equals or is, because equals and is are kind of the same sort of interpretation, that's our mathematical linking verb. It's kind of a requirement to be in every mathematical statement. The same way when I say I, my dog, if I don't include a verb in that statement, it's not grammatically correct. So I have to include that verb somehow. In mathematics, that verb is almost always the equals sign. There's a couple other verbs we can use. And these verbs include the inequalities, which everybody should feel fairly familiar with. Less than or equal, greater than or equal. But also there's this new symbol, which looks like a curved E. So this curved E symbol just means is included in or is an element of. I think that's where the E kind of reflects its element of. But interpret that E as an included in. And so if I jump down here to something like square root of 2 is included in R, this kind of fancy R means the real numbers. Or 3 is included in, and then this fancy n meaning the natural numbers. We can think about those as mathematical statements that have kind of a true or false value. We can verify the grammar of those mathematical statements. So just as I could say 2 is less than 3 as grammatically correct, I can also say root 2 is in R or 3 is in n. Now I have provided a few more examples of grammatically incorrect statements, just kind of ones to get an idea of that we want to avoid. So cosine of 2 pi, of course, is definitely not equal to -2, but what have I done here is I've split 2 pi into 2 copies of pi, and then I've gone ahead and distributed my cosine over the plus, and so that's cosine of pi plus cosine of pi, which each cosine of pi is -1, and say that's -2. So that's just, thinking about math as a language, that's just grammatically incorrect. In particular, it's this equality that is grammatically incorrect. And so it's just good to remember these rules in math on what things you can or cannot do, or what statements you can or cannot make. I got this other nice example here too, where I'm saying I've got 2 6, which we all know is 1/3, but if I split 6 into 2 plus 4 and then cancel my 2's, I actually have a 1 in the numerator and a 4 in the denominator. So that's also not a true statement, but that's because we're violating our grammar, right? And so in some sense, we can think of mathematics as a realm of all possible valid statements, right? The same way we think about English as the realm of all possible grammatically correct statements. I mean, I can make false statements in English. I woke up at 5:45 this morning, just wasn't true. I was asleep at 5:45 this morning. In math, I kind of just include only the true statements as the grammatically correct ones. And then in some sense, we think about applied math as the semantics of the language. So maybe a mathematician isn't concerned with what their statements mean, or at least a pure mathematician is not concerned with what their statements mean. They're simply concerned with whether or not they're grammatically correct. They're asking the question, is this a valid statement to make? It's the applied mathematician's job to verify, and by applying in statistics, physics, computer science, etc., to kind of take the verified statement and then interpret it in the realm of reality, in the real world. So they're applying these statements into the real world. And finally, I finish kind of this section with, our mathematical lexicon, which is also just a glossary, right? If I'm giving a bunch of symbols and their definitions. So we have somewhere to refer to as we're reading our text, as we're speaking, or writing on a blackboard, whatever you want to think. Anytime we're doing math, it's nice, actually, this is like a dictionary. It's nice to have a way of interpreting specific mathematical words. And so what I've done here is I've included kind of the more common ones, even though we will see some others here. I've included the more common ones that we're going to see, and I'll kind of discuss these as we make our way through. So the first one I've already discussed is this fancy E, which we can interpret as is an element of. The second one is actually something maybe you haven't seen as often, but I'm going to try to introduce it in this book and in the entire course, actually, which is the colon and then the equal sign. So I've added a colon in front of my equal sign, and this means something very subtly different than the regular equal sign. The regular equal sign is kind of making a statement about the equality itself, where the colon equal sign is really, it should be interpreted as is defined by, right? So if I, in English, right, jumping back to English, if I define the word glorp is a green, a unicorn, that's perfectly fine. It's not really a true or a false statement in its current collection of words. It's perfectly mathematically correct. But when I use this word is, I don't mean like green unicorns and glorps were always the same thing. What I'm trying to reference when I use that word is that I'm referring to glorp as a green unicorn, or a green unicorn as glorp, right? So I'm giving the green unicorn a new name, and that's perfectly valid in English, but it's not really something that is in and of itself a true or false statement. It's just something that I'm allowed to do. And so that's what this colon equal sign means, that is defined by. We're not really going to question the validity of those statements. They're just something we're allowed to make new definitions to make our lives easier, right? If I'm referring to a green unicorn over and over and over again, I'm just saving myself the effort of saying green unicorn by just saying glorp instead. So that's why we have this notion of the is defined by rather than the equal sign meaning equals. And they both get used in their own context. So let's just give a great example in math where I can say something like a function f of x is defined by x squared. And then because of its definition, when I evaluate that function on the number 2, it's no longer defined to be 4, but it happens to be equal to 4. Right? Once it's been defined as x squared, it delivers the truth of the second statement. That's going to feel a little bit foreign to you right away. You'll just naturally get to it the more we get through these definitions. But of course, we've got our less than and greater than signs. And then I have these lovely, they're called math blackboard symbols, because way back in the day when people would only write math on blackboards, maybe not way back in the day, but before we had typography, like typewriters and so on, we would use these symbols to kind of denote a very special letter. So that's why they had the space in them. You can imagine drawing on a blackboard with chalk, you'd have kind of that open space between them to bold a letter in. And these all have their own special meanings. So we've got the natural numbers n, that's going to be 1, 2, 3, 4. And then if I include that little 0 in the subscript, we're just going to include 0 in the natural numbers. People argue whether or not 0 should be included in the natural numbers all the time. We've got z, which are the integers. So these are every natural number as well as its negatives, including 0. We have q, which are the rational numbers. These are all ratios of integers. So you can build, right? We're building we're building the integers from the natural numbers. We're building the rational numbers from the integers. The next one, these are real numbers. There's an entire class that gets offered, right? It's called real analysis. That really delves into the definition of these numbers. So we're not going to perfectly understand them. Kind of the best way to think about what they are is that these are limits of rational numbers. So if I can take a collection of rational numbers and take their limit somewhere, so mathematically this is called the completion. So if I can complete the rational numbers, then I obtain the real numbers, and that's where things like the square root of 2 and pi show up. These irrational yet real numbers would be. Then we do have the complex numbers. If you haven't studied those yet, we will actually spend a section on them just so that we can feel a little bit more comfortable with them. But these look like x plus I y, where I is kind of this square root of -1, or you can think about it as I squared being equal to -1. And we're going to give ourselves both x and y being real numbers. So once again, we just build kind of each of these numbers from the previous set of numbers. And you can actually continue. There are things called quaternions and other number systems, but they're not really relevant, especially in a calculus context. Complex numbers are incredibly relevant in calculus, which is kind of surprising. We'll see that later this course. Then I got ABC, which I'm going to usually refer to for generic constants. All of these are up to interpretation. They may change a little bit. D can be the differential operator. We're thinking along the lines of like d dx, meaning the derivative, right? That's why I would use D sometimes. E we'll try to reserve as Euler's number, which is approximately 2.718. You probably should have seen that in an algebra or pre-calculus course. F, G, and H are kind of my favorite variables to represent functions. I, of course, we already saw as the imaginary number. J, K, L, M, N. These all usually refer to generic variables that are whole numbers or perhaps integers. And the reason for this is that N, of course, is the first letter in the word number. And then people started working backwards from there, and they were like, well, the second case of a number can be m, the third can be l, the fourth can be k, and j, and so on. So they just kind of gained their popularity as these numbers, whole numbers rather than real numbers. P and Q sometimes are going to be variables in Q, other times are polynomials, other times they're just going to be other constants we use. R we'll try to reserve as a radius, which tends to be a positive real number. S and T are kind of time variables, T for temporal or time variable, S because it's T's neighbor. They're going to be generic variables in R, and they're going to be positive because time moves forward. It tends not to move backwards last I checked. We got X, Y, U, and V's are often generic variables in R. We have Z and W, which are often generic variables in C. Now this is a lexicon. We're not going to be held fast to these, right? We have homophones in math the same way we have homophones in English. So like two mathematical words or symbols can have different meanings depending on context. And so that can get tricky, but I think you get used to it over time. We do have some Greek letters here, alpha, beta, gamma. There's alpha, beta, and gamma, all lowercase. They're often generic constants in R. I won't use them too often. Epsilon I do use a lot, and that's because epsilon is this generic, very small positive real number. People love to use epsilon for small positive real numbers all the time, and so I've adopted that language as well. We have pi, which everybody loves, is our circumference over diameter, which is approximately 3.14159. Theta, the generic angle measurement, we're going to try and always run that in radians, and we're going to try to put it in the range 0 to 2 pi, though that may not always be true, but you can get away with theta as your generic radian angle being between 0 and 2 pi. So we'll try to stick it in there. We've got capital delta over here, which often represents change. We will see that eventually. We've got infinity, which is not actually a number, but it's a useful symbol, a useful concept. So it doesn't interact with any of these plus, minus, times, or division operations. So that's just something to keep in mind. A lot of people like to include it with those operations. It's not possible. It occupies its own space, its own mathematical space, independent of those. We've got these intervals, right? This is interval notation. Now this first one may look like a point as well. That is the same notation we use for x, y coordinates. And so this is what I mean by homophones. We have, two mathematical symbols which mean different things. They are the same set of symbols, but under context they mean different things. Here we're talking about interval notations. These are going to be the real numbers greater than a and less than b. And of course we can close one side, which just means you include that side. So in the second case include a but not b. In the third case include b but not a. And in the last case include both a and b. So in terms of a number line, right, think about a to b, this would be the closed interval AB. Then this is a slightly new one that maybe you haven't seen before. If I put double brackets around some entries, and this is where you can see I'm using the difference between A and B and M and N, these are actually going to be like a whole number interval, right? So the integers between these 2 points and including the 2 points. So rather than thinking about a continuum between A and B, we now have like n plus 1, ... and then we've got m minus 1 and n. So they're kind of discrete elements. These are like different points in space. So maybe a different way of describing this, if I have -2 to 2 with double brackets, that's going to be the set -2, -1, 0, 1, 2, those 5 numbers. Of course, we have our plus minus divided and multiplication. Everybody feels good about those. Exponentiation of a specific base, right? The power is defined as repeated multiplication, the total power number of times. The logarithm of base x says, let's do the opposite of the power, right? So I'm going to put the x in the denominator, and if that x the log of x runs into z, then what it's actually interpreting, if this is equal to a specific number, we're interpreting this as whatever the specific number was, which would give you z when you take x to that power. Logarithms have always been kind of a tricky subject matter. We will cover them again later. We got the yth root of a specific real number. That's just going to be interpreted as 1 divided by y in the power. So if we're happy about powers, then we're happy about roots. And if I don't put a 2 on my root, or I don't put a y, just interpret that as the second root, which is the same as always the square root. We have sine and cosine, which for the purposes of this book we're defining as the y and x value respectively of the point on the unit circle, whose angle with the positive x-axis is theta, right? And so rather than thinking about SOHCAHTOA, which we'll see in our trigonometry section, SOHCAHTOA is a valid definition of sine and cosine, but it doesn't account for negatives. It kind of SOHCAHTOA only gets you in the first quadrant of the unit circle. The sine and the cosine are going to give me the x and the y coordinate of a point on the unit circle. So cosine will be the x coordinate, sine will be the y coordinate. That's a safer way of defining the two of them. Tangent is the ratio of sine to cosine, cotangent the ratio of cosine to sine, secant 1 divided by cosine, and cosecant 1 divided by sine. And finally, since this is a calculus book, ddx, meaning the derivative operator, which takes a function to this particular quantity, which is kind of call it the limit of the difference quotient, right? But that is how we define the derivative. So this is a great example of us actually using that definitions equal sign. These aren't equal to each other based off of some, universal property of truth. They're equal to each other because we've decided that we're going to call this, because it's annoying to write it down, by the name d dx f of x. That's the only reason why we have d dx f of x. It saves us time from writing down this crazy long limit of a difference quotient every time we write it down. So that's great use of the definitions equals. Same with the next case when we have the integral, which we just define as the antiderivative plus a constant, right? So I'm saying it's any antiderivative f where the derivative of f happens to be equal to lowercase f. So here, once again, we've got the definitional equal sign, right? Because I'm saying this collection of symbols is actually defined as this object. But then in the second case, I have the real equal sign because I'm saying now this object is no longer defined to be the antiderivative f. It needs to satisfy that it's the antiderivative f. So this is a question, like, is it true or false? Where the first one is, no, I'm giving it a new name. So that's the difference of those equal signs. In our next subsection, we're talking about something I like to call pseudo-mathematics, which is kind of a stark reality of referring to math as a language. And that's that it's incredibly tedious to operate and communicate mathematics as its own language. We really communicate all of our math ideas in a balance of precision and rigor, which really balances the mathematical language with the English language. I mean, there's a reason I'm talking to you in English right now. Can you imagine if I was saying only math to you and it were just 1 minus 17x plus x squared equals 34? X equals negative 2.104, and it would get incredibly annoying really quick. So what I end up doing instead is I sprinkle mathematics within an English kind of umbrella, right? The English is what allows us to communicate. The mathematics needs to be there to be rigorous when we need the rigor, and so we just get, this is what I call pseudo-mathematics. It's right, it's this balance of an English umbrella along with sprinkles of math popping through to keep us kind of grounded, make sure that what we're doing is still true. I've got these examples of translating math into English. It's pretty straightforward. If I wanted to interpret this mathematical statement as English, how would I say it? I would say, well, the integral of 3x squared minus 4x is equal to x cubed minus 2x squared plus c. So that is a collection of English words which refers to the mathematics. And you can do the reverse as well, right? We could start with English and end up going to this mathematical collection. But the real benefit of starting with English and going to math is that there are a lot of English statements we can make which themselves feel like they have mathematical solutions. But they're maybe not straight math the way that this integral above was. So here I've got the cities of Aliceville and Bobtown, which are 100 miles apart from each other. If train A leaves Aliceville for Bobtown at 2 p.m., traveling at a speed of 25 miles per hour, and train B leaves Bobtown for Aliceville at 2:15, traveling at a speed of 35 miles per hour, at what time will the two trains begin to pass each other? Right, that's a fairly straightforward English statement. You can tell there's math hiding beneath it, but it's not really meant to be in math right away. This is kind of the case of word problems that people tend to hate. But what they tend to hate, I think, is the translation aspect, right? This translation of being able to interpret an English statement as a mathematical statement is kind of the part that's crazy that we need to get better at. And so what have I got here? So there's my English. I've translated it to math here, and I've said A equals 25t minus 2. Where is this coming from? Aliceville train is traveling at 25 miles an hour. T starts at 2 p.m. So at, when t equals 2, we have t minus 2 is 0. So it's moved 0 distance away. Bobville starts at 100 miles from Alicetown. Bobtown starts 100 miles from Aliceville. It itself moves at 35 miles an hour, but it starts at not 2:25, but actually 2:15 p.m. because of the weird way that clock numbers work. 15 minutes is 0.25 hours. And so what we're going to do now is solve the value of t, which gives a equals b, right? And this is kind of the power of translating from English into math, is that the moment we see this, we've translated to math, we can just use this mathematical grammar to give us an answer of an English statement. Right? If we want, we can answer the English statement. We could try to answer it just in reality, but by translating it to mathematics, we can use the rules of math to give us an English answer. And so now that we know that, we just run some algebra and we get our answer, which, by the way, is 3:48 p.m. that they cross each other. But I do need to note that the translation is not unique. Totally fine to translate it in multiple different ways. And then I just provide my interpretation of how I actually translated that English into that math. But you can translate it however you want. But even though I called this English to math, in reality, this math at the end is not quite pure math, right? I've got this English statement at the bottom, solve the value t, which gives a equals b, and I even use the English word and there. So this is what I mean by pseudo-math. Right, the pseudo-math that's going on here is kind of the correct balance of an English and a math statement. It's not pure math. If I wanted pure math, I could write something like this. T is in the set which contains s being positive numbers, such that 25 times s minus 2 equals 100 minus 35 s minus 2.25. Now there's only going to be one specific t in this set if you actually work out what's inside the set, and that's the same t we would have arrived at before. But in this case, I've translated 100% into math. The big problem is that it completely loses its meaning. Right? We don't want to go so deep into the mathematics that we lose our meaning. We want to go deep enough that we can see the grammatical rules show up, which is what we want to use to arrive at our result. So we're going to consider one final setting, which is kind of both translating the math and English into their own versions of pseudo-mathematics and see them merge in the middle so we have an idea of what it means to properly understand pseudo-math. So here I'm going to start with a mathematical statement, which I don't really expect you to be able to translate yourself. So I'm going to work through this translation in front of you. And what this is saying, these curly brackets mean a set, so a collection of mathematical objects. We've got k's and l's in the integers, so positive or negative whole numbers, such that, it's a vertical bar there, that root 2 equals k divided by l. And I'm claiming that this set, so the set of integers which satisfies this property, is equal to that 0 with a slash through it. That's called an empty set, meaning it's empty. So I'm not really going to say that. But what I say in pseudomath instead is the set of all pairs of integers, k and l, for which root 2 is equal to k divided by l is empty. Not bad. At this point, since I'm in pseudomath, I can actually reinterpret the pseudomath. And I can say, rather than saying is empty, I can say there are no pairs of integers k and l for which root 2 is equal to k over l. And that's a very nice pseudo-mathematical statement to make. And it also is properly telling me what I'm really trying to enforce here is that you can't take two ratios of integers and recover the square root of 2. So if I go from a different direction, starting with English, which is in pure English, the square root of 2 is irrational. And maybe I want to prove that statement. It's going to be hard to prove just in the English language, so I want to translate it into pseudomath so I understand what it's actually trying to say. Well, what I do first is I take this word irrational and I switch it with not ratio of two integers. That's my translation. And the square root of 2 I translate as, the mathematics square root of 2. And the moment that I have it in pseudomath, I can actually, go one step further, and I can grab ratio of two integers and actually replace it with a true ratio of two integers. And now if we look and we see this, root 2 is not equal to k over l for any integers k and l, and we look at the top here, my other translation, there are no pairs of integer k and l for which root 2 is equal to k over l, we can tell that these are actually the same statements. And so if now I want to interpret the original purely mathematical statement in a purely English context, because I've translated through pseudomath, I can, and I know that that original math statement is referring to the square root of 2 being irrational. Now, like I said, this is not something I expect anybody watching this to necessarily understand. It's just me trying to emphasize that translating into pseudomath is probably the most powerful thing we can do, both from an English statement, but also from a math statement. The pseudomath land, that balancing act, is where we want to interpret everything. And so that's all I have in this finishing statement. I say we reassure the reader they're not necessarily meant to understand the mathematics in each of these examples. Rather, what is important is that the reader does understand the utility in translation between our languages. So think about mathematics as a language. Understand that it can be translated back and forth between English, but the sweet spot is kind of this balanced area where you're able to apply the grammatical rules of math, which are regular rules of math, and at the same time allow yourself a semantics, an understanding of what it's actually saying. So wherever that sweet spot is, try to find it. And once you do, I think it'll make a lot of other mathematical problems easier for you. So anyway, I'm going to stop there for today. Thanks for hanging in there with me. I'm excited for this course with all of us, and I'll see you in the next one. Bye.